Welcome, my name is Shlomi. In this video, I'm going to show you how to connect to the Bitcoin protocol. We are going to find another peer on the network, another node on the network, and we are going to send messages to that peer. Quite a substantial part of this video will also deal with the concept of messages in the Bitcoin protocol, because the Bitcoin protocol, like many other protocols, uses messages in order to communicate. For example, I can send a message to a remote node on the network, to a remote machine, a remote peer, and ask for a specific block or for some sort of a specific information. The main goal of these video tutorials will eventually be to construct a transaction. And a transaction is basically a specific message as well. So we're going to go over the concept of messages in the Bitcoin protocol. It's quite important to understand how the Bitcoin protocol handles those messages, because it might be a bit different from what you might be used to if you are familiar with networking from another protocols, like from TCP/IP, for example. So we're going to see exactly how to construct a Bitcoin message and how to work and understand those messages. Now, before we start, there are 4 concepts that I think you should be familiar with before we can move along. Those concepts are bit and bytes, little endian versus big endians, ASCII, and hexadecimals. I'm going to post links to some videos in the description below. I believe these videos should be more than enough in order to understand those 4 concepts. If you're not familiar with these concepts, then I suggest that you will try and watch those videos before you before you keep on watching this tutorial, this video. Before we start, I want to show you a few websites. The first one is bitcoin.org. This website, it has 3 sections. It has more than it, but we're going to use 3 sections, which are the developer guide, the developer reference, and the developer examples. There is also the Bitcoin wiki site, and this site contains it has very good examples and a lot of technical information. I find this site very useful. I might also add a few more websites which I find very useful in the description below, so make sure to check it out. Okay, and that's it. Now we're actually going to start to connect to the Bitcoin network. So let's go back to the bitcoin.org website. Let's go to the developer guide. Over here, under connecting to peers, you can see that connecting to a peer is done by sending a version message. This message contains my version number, block, and the current time. This message will be sent to the remote node, and if this message is correct, if there is no mistakes in it, then the remote node will respond with its own version message. You can see that there is a bit more to it. The remote machine might send me more messages than just the version message. But for the purpose of these tutorials, we only want to be able to establish a very basic communication, and we want to use this communication to send only one type of message, which will be eventually the transaction we want to send over. Then the version message will be enough, and I'm just going to ignore the other messages. Again, when you are more familiar with the concept, with the protocols, and you want to improve your understanding of the protocols, then you need to come back and try to work with the other messages as well. If you want to send a simple transaction, then version message will be enough. Okay, so let's start working on our version message. Over here, you can open the version message. So, over here, we have an ordered list. The order is very important, of all the fields which construct the version message. We have the bytes number. This is the size of each field. And we have a description, which describe what type of information this field holds. Now, don't forget that a message is basically a very long string of bytes. The machine on the other side, it knows exactly how many bytes and in which order it should expect them. For example, it expects that the first 4 bytes will be a version message. So it will cut the first 4 bytes, and it will say, okay, the first 4 bytes, they must be some sort of an integer, and that integer will tell me what is the protocol version number. Then it will start looking at the next 8 bytes, and it will see that it's supposed to be some sort of an integer as well, and it will give it the service code. Let's see what is below. We got timestamp. It will look at the next 8 bytes, and it will say, okay, this is supposed to be an integer, 8 byte long, and it's supposed to be the timestamp, and so on and so forth. So once again, the order is very important. The size of each field is also very important. Don't try to mess with it. Okay, so let's go to our code. I have already created a folder. I called it my Bitcoin. You can call it whatever you want. And I'm going to create a file. I'm going to call it connection. Connection.py for Python. Now I'm going to import a module which called struct. Import struct. Here we go. Well, this module, I opened its documentation page already. It's over here. You can see I'm using Python 2.7. This module will allow me to pack information in a very specific size and order. So for example, if I have an integer, let's say this integer is 3, and I want to nest this integer inside of a variable, and I want to make sure that this variable will be exactly 4 bytes long, and then basically this module, that's what it will do. It will make sure I will have an integer and it will be no more than 4 bytes long. Most of the time, we are going to use the pack function over here. And you can see we need to insert a format and a values. Now the list of formats is down here below. You can see over here we have big endians versus little endians. Later on it will be quite important. And over here we have a list of all the types of variable we might insert: integer, string, floats, boolean, etc. and their size. We are going to use unassigned most of the time. And we already know that the first, you already saw it in the developer reference, that the first 4 bytes going to be the version number. So we need to find an integer which is 4 bytes long, and that is unassigned. So we are going to take this one over here, capital L, unassigned integer 4 bytes. I'm going to make version equal struct pack. We got timestamp. The format is capital L for 4 bytes integer. And now we need to find the version number. So let's go back to the developer reference. We can see in the description that there is protocol version. You can see it in the protocol version section. It's over here. Oh, it's over here, yeah, second. So this is the integer we are going to insert over here. And that's it. We just created the first field of our version message. The first field is 4 bytes long, and it contains the version protocol number, and this number is 70,002. Now we already saw the next line should be services, and it should be 8 byte long. Okay, cut. So let's have a look at the documentation. For 8 byte long, it should be an integer. I also saw it. You can see it over here. Services, integer, supply the transmitted node, 8 byte long. 8 byte long integer. So over here, unassigned integer, 8 byte long, it's capital Q. One second. Capital Q. Now we just need to find what type of integer we are going to insert. What is the actual services code we are going to insert? So let's go back to the developer reference. Developer reference. No, sorry. Yeah, this is the developer reference. And it says a list of services code below. See the list of the services codes below. Let's go down here. Here we are. We can see the following services identifiers have been assigned. Now this field, it basically says what type of node we are running on our machine. And basically it means either we are running a full node or non-full node. And it tells the other machine whether it's whether we have the full blockchain, whether we have some sort of filtered information on our machine, etc., etc. And if we say 0, this node is not full node, we give it 0, unnamed. then the other machine knows, well, it shouldn't really bother with asking any other information from us. It won't even try to ask information out of our node. It won't ask for a list of other peers. It won't ask for other blocks, etc. And because we're making a very, very simple node right now, we are going to define it as a 0. This node is not a full node. So let's go back to the code. 0. And yes, Sublime Text might ask you to pay them, and I think you should pay them because they are really, really good, and I will pay them. I will. So the next 8 bytes should be the timestamp. So timestamp struct pack. We saw it should be 8 bytes long. If you forgot, you can go here. Here it is. After services, 8 byte services, we got 8 byte integer timestamp. And this is the current timestamp. So in order to insert the timestamp, I'm going to use a module called time, and a function called time. Let's import this module. Import time. Okay? So over here, we have the current Unix timestamp, and it is packed inside of an 8 byte long integer, 8 bytes long integer. Let's see what the next field is. Okay, let's remove this one. Cool. Now you can see that the next 3 fields needs to provide some sort of information about the receiving machine. When we are talking about the receiving machine, we are not talking about the other node, but we are talking about our own machine, how to connect our own machine. And you can see, if we scroll down a little bit, that after that, we have another 3 fields, and the other 3 fields, they basically require the exact same information, the services, the IP address, the port, only this time of the transmitting machine. Before that, it asked this information about the receiving machine. We are receiving port, receiving IP address, receiving services. So basically over here we provide information about the machine that will transmit our message and the machine that will receive information from the other node on the network. Both the transmitting machine and the receiving machine, at least in our example, going to be our own local machine, our own local host. If you understand more about networking, maybe you want to do something a bit more fancy. Maybe you want to make sure that every message that is received will be routed to another machine on the network. Maybe this machine has more storage capacity, or it, I don't know, has some sort of better hardware. Again, it's up to you. But for the purpose of this video, both the receiving and the transmitting will be exactly the same machine. It will be the local host, and it will provide the same services, which are basically none at all. So again, let's see. Right now we need to insert the information about the receiving machine. So the first 8 byte should be address receive services. Let's go back to our code. Address receive services. Yeah. And this machine also, it doesn't going to provide any type of services, so we are going to insert 0, just like before. It should be 8 byte long. Struct pack capital Q for 8 byte long, and 0 for no services at all. And you can also see this is basically, it's exactly the same field as this one. So I'm going to leave it here as a comment. It is exactly the same field. I want this code to be very, very redundant, so people might be able to print it and go through it. This is why I'm going to insert this line more than once if needed. But again, this is just this services variable over here. The next line is the address receives. The next line is the receiving IP. Address receive IP. We're going to struct pack. Now pay attention, there is a small catch here. You can see it should be 16 character long, 16 character long, in big endian byte order. So we need to insert our IP address as a 16 character in a big endian byte order. Okay, so let's go over here. We can see that for character, we're going to use S. I'm usually using S. And for big endian, over here, we are going to use the greater than sign. Okay. So the format is greater than 16 character. This is big endian, 16 characters, and we are going to insert it as a string. The localhost IP address is 127.0.0.1. Now, for most cases, your localhost IP address will also be 127.0.0.1. If you know more about networking, you can change it a little bit. Again, I suggest that for the purpose of this video, keep it like this, keep it as simple as possible. Let's see what is the next field now. Over here, developer reference. And we can see that the next field is the receiving port. It's 2 byte long, integer, and again, big endian. Okay, so let's see, we already know how to do big endian, but 2 byte long integer should be capital H. Okay, so address receive port struct pack big endian 2 byte long integer, and I'm going to use port 8333. This is the default port for the Bitcoin protocol. I suggest you don't try to change it, at least not in this stage. Now, as we saw earlier, the next 3 fields, over here, the developer reference, yeah, the next 3 fields are the information about the transmitting machine, which in our case, it is exactly the same machine. So we're just going to copy paste the last 3 fields. Copy paste. Here we are. And we're just going to change it from receiving to transmitting, only because we want to make sure that it is readable and that it will be, it will be easy to work with. Over here. Transmitting. Cool. This is it. Right now we have all the information about our machine, about the machine that will send messages, and about the machine that will receive messages. Let's see what the next fields are. Okay. So the next field is 8 byte long, nonce. This nonce is a random number which help a node detect a connection to itself. Basically, this type of message, it's some sort of this type of field, is some sort of an identification number. It helps the other machine to, it has some sort of a serial number for our connection, so it will be easier for that machine to communicate with our machine. It is quite useful if you want to keep the connection open for more than 30 minutes, and you will see it has something to do with ping and pongs, but we're not going to go through it at the moment. Still, we need to assign this variable. So, 8 byte long random number. Let's do it here. Nonce equal struct pack 8 byte long integer, capital Q, and I'm going to use a module called random and a function called get rand bits 64. This function will provide me with 64 random bits, and 64 bits is of course 8 byte, so that's it, that's exactly what you want, 8 byte long random number. Let's just import this module, import random, here we go. Now let's have a look at the next field. The next field is the user agent. You can see it's actually 2 fields. It is the user agent bytes, and it is the user agent itself. This is basically the next fields we need to fill. The user agent is some sort of a vanity plate. It tells the other machine what type of node I am running, what type of a specific node I'm running. In our case, we don't run any specific code. This is something we just build in our own home, so we are going to keep it empty. Now you can see that the user agent might vary in size. And the Bitcoin protocol, it actually does it quite often. You might see that there are many fields that don't have a predefined size. So we need to give the other machine some way of knowing exactly how many bytes it should expect right now. The machine, it already knows the first 4 bytes should be for a version protocol number, next should be 8 bytes long for the services code, another 8 for the timestamp, and so on and so forth. And then it knows that the next variable, the next field I'm about to receive, this field will contain a specific information, and this information will be the length in bytes of the fields after that, the next field. In our case, the next field should be empty. So we're just going to tell the other machine, the other node, you're going to receive an empty field, and just, I don't know, skip this one. Go right next to the one after that. So let's do it. User agent bytes struct pack. Now I want to find the smallest integer possible, because it's going to be just 0, and we don't need to provide any more information, and we are not required by the protocol to keep it in a specific order and size. So I'm going to make sure that this is going to be the smallest integer possible. Let's go here. The smallest integer on a sign is capital B, only 1 byte long. B and 0, because the user agent is an empty field, so just skip over this empty field. Go to the next field. Let's scroll down a little bit. There we are. And let's go back to the developer reference. In the developer reference, you can see that the next field is starting height. It's a 4 byte long integer. The starting height is basically the number of the highest block that our machine is aware of. We're going to insert it manually in a second. Just starting height struct pack, and it was supposed to be 4 byte. We just said, yeah, 4 byte. So 4 byte is capital L. 4 byte integer is capital L. And now you can go over here. I'm using Blockchain Info. It's a great website. It provides a lot of information about the Bitcoin network. And you can see that the highest block, this is the highest block. So we're just going to copy paste it. That's it. This is the highest block we are aware of. And the next field, you can see over here, it's the last field as well, is the relay. It's only 1 integer long, a boolean. Basically, it's a flag. We're just going to tell to the other machine. If it's going, we're basically just going to tell to the other machine. You can say how cooperative we are. If you give it false, if we give it 0, then the other machine will just know that there is no use in trying to transmit any transaction to our machine, because our machine it won't deal with them. It's not going to propagate those transactions. It's not going to save them anywhere. It's just going to ignore them. And yes, we are going to ignore any type of incoming messages, because again, we only want to send our own very, very basic transaction message. So back to the code. Relay struct pack. For boolean, it's a question mark. You can see it over here. Here it is. It's very easy to remember, just a question mark. And false. We're not going to, there is no point in transmitting transaction to us. We're not going to propagate those transactions, or we're not going to try to process them in any way. That's it. Back to the reference. You can see right now in the reference that basically we just completed. So basically, as you can see, we just finished to construct our version message. I just want to make sure it's all organized, so I'm going to insert all of those fields into one integer, so it will be easier to work with. Back to the code. I'm going to call this variable payload. You will understand why in a minute. And now we are going to insert all the fields one by one according to their order. So the first one was version. This is 4 bytes long. Then we got services. This was 8 bytes long. Then we got timestamp, another 8 byte. Then we got, this is for the receiving services, yes. Another 16 for the receiving IP. And another 2 for the receiving port. Now another 8 for the transmitting services. another 16 for the transmitting IP, and another 2 bytes for the transmitting port. After that we got 8 bytes for the nonce, 1 byte long for the user agent. This is this type of field basically contains 0. It basically tells the other machine, okay, skip this field, it's irrelevant. The starting height, which is another 4 byte long, and 1 more byte for the relay. And this is it. This variable payload, this is actually the version message. This is what we want to send. Now, before you can send it, there is one more catch. The Bitcoin protocol, it uses a different header than what you might be familiar with if, for example, you are working with the TCP protocol. We need to make some sort of a header. We need to make some sort of a title. This title will contain some sort of a specific information, and the other machine, before it will even start reading our version message, it will look for this title. And if it won't find this title, or if this title won't be correct, it will be damaged in any way, it will be corrupted in any way, then the other machine will say, you know what, I'm not even going to read your message, I don't care, I'm just toss it away. So it's very, very important to understand that before we can send this message, we need to make this message, we need to make the header for this message, we need to make a title for this message. So let's have a look at what a Bitcoin header looks like. And now we are going to go to the wiki site. You can see we have a protocol documentation over here, and we got a message structure. So right at the end, we can see the payload. The payload, this is basically the variable we just constructed. We call it payload. And the payload, it's the actual data. This is basically our version message. And before the payload, there are 4 fields. And those 4 fields, they are the header, they are the title. The other machine won't even start reading our actual data unless it has these 4 fields. They need to be correct, they need to be in the right order, the right size, etc. So the 4 fields are 4 bytes for the magic number, 12 for command, 4 for length, and another 4 for checksum. Now, the first 4 bytes is the magic number. The magic number is some sort of an identification of the network. It tells the other machine that right now we are going to use the main network. There are more than one option. There is the main network, there is the testnet, there is the Namecoin, but we are working with the main network. So the mainnet is the most predictable network. This is the one we are going to work with, but I suggest to be quite cautious when working with the mainnet. The mainnet, this is where you might actually lose real money, real coins on this network. On the testnet, they reset the network once in a while, so it's not that dangerous to work with the testnet. And I suggest that once you completed those video tutorials, if you want to improve your understanding of the Bitcoin protocol and you want to tinker with it a bit more, then take another step and learn how to work with the testnet. But we're going to use the mainnet, and the mainnet, the magic number for it is over here, F9BEB4D9. Back to our code. Magic. Let's copy paste it. Let's organize it. Now this is already 4 bytes long, so I'm not going to pack it. I'm just going to decode it because this is hexadecimal, so we want it to be decoded. Okay, so now let's go to the next field. The next field is 12 characters long. It's in ASCII, and this is basically the name of the commands we want to send. And we need to make sure that if the name of the command is less than 12 characters, for example, version, it's only 7 characters long, then we need to insert another 5 more characters, and those other 5 characters should be null. Here it is, null padded. Again, it has to be 12 characters long, no matter what, and it has to be padded with null. Okay, so let's go to our code. Command and should be version. This is the command. This is 7 characters long, so we need to insert 5 times null. This is how you represent null in Python. In Python, this is those zeros. That's null. Cool. Let's go to the next field. The next field is the length. The length of the actual payload of the actual data should be 4 byte long integer. Okay? So, length, equals len of the payload, and we need to pack it, of course, so it's going to be struct pack, not payload, pack, and it should be 4 byte long integer, so L, here we go, now it's packed. And now let's have a look at the last field. The last field is checksum. Checksum, we basically need to take our payload, our actual data, and we need to use some sort of a mathematical function called SHA-256 over that payload. The result will be some sort of a very weird string, and that string we are going to use the function SHA-256 on that weird string again. We are going to SHA the payload twice. We are going to SHA-256 it once, and then you are going to do the same process again. The machine on the other side, it will also take our actual data, the payload, and it will also going to SHA-256 it twice. And only if the result matches, only then it will say, okay, this is the actual message. Nobody tried to tamper with it. Nobody tried to corrupt it. It wasn't corrupted in any way. I can read it. This is the real thing. So let's do it. We are going to create a checksum. And there is a module called hashlib. And this module has the function SHA-256. So we are going to SHA-256 the payload. We need to digest the result. Digest basically means that the results need to be digested either to hexadecimal or to binary code. Depends exactly on what we want to achieve. We need to take this result and we need to hash it again. So let's hash it again. Hashlib SHA-256. You can see we are hashing the result. We need to digest it, of course, again. We want to have some sort of we want to get the 4 bytes out of it. And it should be only 4 bytes long. This one over here will basically take only the first 4 bytes, because that was the requirement. The first 4 bytes. Cool. Okay? Basically, right now, we have all the information that is required in order to construct our version message. We have the title, we have the data itself. Let's just make the message. So, message. The message is the magic number, command, length, and checksum. Those 4 fields, this is the title. Those 4 fields are the titles. Of course, I don't need this plus sign here. And the payload, this is the actual data. This is the actual message itself. The actual data, the title. And this is it. Right now, we have a complete message with the header, with the title. All we need to do is to actually send this message. This message on the Bitcoin network, well, let's do it. But before we do it, we need to also import the hashlib module. I forgot to import it. So, import hashlib. Cool. So, in order to send a message on the network, we need to import another module. Let's go. Import this module called socket. And this module will basically give this type of Python code, this Python program, will give us the ability to go online, to get connected to the network. So now we are going to create just one object which will allow us to go online. I'm going to call it S. It should be a socket, socket module, socket. And now we should insert socket.af, sorry, INET, and socket SOCK, yes, stream. If you don't understand this line, it's okay. This line is only meant to allow me to go online with this S object which I just created. Just copy this one if you don't understand it, and later on you can start to look for more information about this module, about the socket module in Python, but it's a bit irrelevant at the moment. Now we need to find host and port. This is of the remote machine, of the other node on the network we want to connect to. I will show you how to find this information in a minute. We want this S object to connect to this host and port. Once it's connected, we want it to send the message we just created. And we also want to be able to receive information from that node. I think 1 megabyte, this is the maximum amount of information it might receive. It's more than enough for the purpose of this tutorial. So now all that we have to do is to find the information about the remote machine, the other node, the other peer on the network. We just need to find its IP address and its port number. So let's go back to blockchain info. And over here at the bottom, you can see 446 nodes connected. Let's go down here. And over here it gives you a list of all the other nodes it is connected to. And you can see it has a list that contains the IP address of that node. It contains the port. You can see all ports are port 8333. So again, you stick to this port. There is really no reason to change it. And the client version, they are all running the same version, which is the 70,002. Yeah. And this is it. So let's just take the IP address, the first one. You can try whichever one, whichever IP address you want. I'm just taking the first one. Let's put it here. It should be the string. And we already saw that the port is 8333. And this is it. Those 54 lines of code with lots of spacing and redundancy between them. This is all the line of code, this is all the code that is required in order to construct a version message and send it to another node on the network. Once this other node will receive our version message and confirm it, we are basically part of the network protocol. We are basically part of the network. We are basically part of the Bitcoin network. Okay, so let's send it. Now I suggest you have some sort of a network analyzer. I use Wireshark, which is not only free, but it's also very, very convenient if you're using it with the Bitcoin protocol, because it has its own built-in Bitcoin parser, which will provide you with a lot of very, very useful information about Bitcoin messages, and it might give you a lot of valuable information if you want to do some sort of debugging or learn more about the protocol. Okay, so let's open the command line. And now it's time to actually send our message. So let's hope it's all going to work as expected. Python connection, we called it. Yes, connection.py. Let's cross our finger and hope we're not going to get any error. No error, yeah, cool. As you can see, we just sent a version message and we received another version message, and we also received 2 more messages that we are now going to ignore them because it's a bit irrelevant at the moment. And you can also see here at the bottom there is some sort of a tab, Bitcoin protocol, and this tab provides a lot of information about the Bitcoin protocol. It already passed the information. You can see it has the magic number, it has the command name, the length, the checksum. This is the title, this is the header, and the version message itself. We can open it here, and it provides us with a lot of information, the protocol version, node services, timestamp, address as receiving node, blah blah blah, random nonce, etc., etc. And that's it. Right now, we are connected on the Bitcoin network. In the next videos, I'm going to show you, we're going to talk with you about private keys and public keys and addresses. That's going to be the next step. That's it. See you later.